Okay, good evening everyone. I am Shivani Dhok and I welcome you all for the week 6 tutorial for the course of Simulations of Communication Systems using MATLAB. This tutorial will be divided into two parts. First, we'll have a quick recap of week 6 content and followed by some questions which are related to week 6 content. So let's start with a recap of the content. So this week was also completely focusing on random processes. But before going ahead, we looked at the need of having stochastic models and other things. So we started with what is known as the practical signals. So to understand this practical signals, four examples were given, which included images, then speech, climate data, and economic indices. So we said that all of these four are of importance to us. However, if we look at images and speech, these are important to us in communication perspective. So these are important in communication, or let's say I'll write it in this way, important for communication. And this remaining ones like climate data and economic indices. So these are basically practical data. These are important for some other aspects, maybe weather forecast or let's say portfolio management and other stuff. However, this is not useful for communication. And our goal is to understand how or to model communication systems in MATLAB. So we will be focusing on these kind of data. Now this data, whatever we are having here, is highly correlated. A simple example is if I have an image, let's say I have an image and I have someone's face here. So if you observe that this entire part, let's say, is colored in green, and you can divide this entire image into small pixels, dotted lines, okay, like this. So if you observe, the pixel here and here will have similar values. Because both have same colors. Or even if you have the photo of your face, then your let's say your eyes, or let's say your eyeball will be represented by multiple or large number of pixels. So each of these pixels are somehow related to each other. They will have some common properties, which means that this data that we are having will be highly correlated. And we need to develop stochastic models to take into consideration these important signals. So these practical signals we need to handle, and in order to handle these signals we need to look at stochastic models. So first we looked at what do we mean by models. So we looked at its definition. It said that this is any hypothesis so these are any hypothesis that will be useful let's say that is useful to explain or describe these or variations or the hidden laws that govern uh, these physical data. Okay, and basically we need to develop these models. So we need to develop these models, or we need to develop stochastic models for communication system that will lead to optimal performance. And this performance optimality, we'll look into it after a few lectures. Okay, so for stochastic models, we looked at different approaches. The first thing that we looked at was autoregressive process. So this autoregressive process, let's say autoregressive process of order m is given by xn plus a1 conjugate x of n minus 1 and so on till am conjugate x of n minus m, which is equal to pn. So what do we want to model? Basically, we have an input which is v of n. We'll pass it through an LTI system, and we will get an output that is x of n. And this particular v of n that we are having here is a white process. When we are saying white, it means that vn1 and vn2 are completely uncorrelated when n1 is not equal to n2. So this is a white process. However, this xn that we are obtaining here will have a correlation structure. So the output of the LTI system will have a correlation structure. And one such approach that gives us this as an output is autoregressive process. And this equation or this difference equation which I have written here is the difference equation for m order sorry m order autoregressive process. Now there are some properties of this, and in order to understand the correlation properties, we had considered autoregressive one process initially, and after that we looked at the end we looked at something known as Euler-Walker equations. We'll look at it afterwards. But for AR1 process, which means that AR1 means your m, this capital M, is equal to 1. So here your m is equal to 1, and for that we can write the difference equation something like this: xn equal to axn minus 1 plus bn. And we looked at some statistical properties of this thing. So we saw that this is expectation of xn square comes out, or we take it as sigma x square, and this comes out to be equal to mod a square sigma x square plus sigma v square, where sigma v square is the variance of this Vn. Then we looked at expectation. All these derivations are there in the lecture. I won't go into details of it in the interest of time. This comes out to be equal to a into sigma x square, and expectation of x of n into x conjugate of n minus k. This comes out to be equal to a to the power k into sigma x square. So this is what we are having here for autoregressive process, and this particular these particular properties we have obtained for AR1 processes. Okay, so once we have this thing, so once we have looked at what is known as autoregressive process, the next thing that we looked at, the next thing that we looked at was MA model, or in other words, this is moving average model. So this moving average model, my output x of n is written as this white noise of that particular current instant plus linear combination of k previous realizations of this noise process. So this correlation thing is coming due to this addition of previous noise realizations. Okay, and the correlation for this, we had obtained as, there is a BL conjugate also. So this we had obtained as B of L convolved with B of minus L. Okay, so all of these things we have seen in great detail in lecture. I won't go into more detailed derivations because we need to solve some questions related to these. And at the end, we looked at what is known as ARMA model. So this ARMA model is basically combination of two. So we have AR, that is autoregressive, and we have MA, that is moving average, and combination of these two is basically my ARMA model. So what it says is, or the difference equation for this particular thing is something like this. So we have x of n plus m previous instances of, or weighted instances of, output, and this is equal to your input current instant plus previous k instances of, or weighted instances of your input noise or input white process. So this part here, let's color code this. So this part here is basically your autoregressive model, and this part here is basically your moving average. So this is your ARMA model. Okay, after that we looked at what is known as Wald decomposition. So this Wald decomposition says that any wide sense stationary process let's say xn, can be decomposed into two independent processes. First one is predictable process. Let's say it is given by S of n. And second one is your innovation component. And let's say this is your V of n. Okay, so this we have here. So what we want to do is we want this decomposition in a precise way. So this is just something that we had stated in the lectures. After that, we looked at some interesting thing, that is Euler-Walker equations. So these equations basically are for your autoregressive model. And let's say my autoregressive model is something like this. Xn equal to summation k equal to 1 to m, some weights wk, conjugate x of n minus k plus vn. Then your rxx of L is given by summation k equal to 1 to m, wk conjugate rxx of n minus L plus sigma v square delta L. Okay, so this is what we are having here. And now this thing we can write something, we can vectorize this like this. And then this can be written as something getting multiplied by your weights, that is w1 conjugate, w2 conjugate, and so on till wm conjugate. And we can fill in the entries that are here. Let's say it is rxx of 0 and so on till rxx of m minus 1. And similarly, I'll have rxx conjugate of m minus 1. So basically, this is a Hermitian symmetric matrix, rxx of 0. And remaining we can fill in. So we wrote this thing as P. This is, let's say, R, and this is W. So you have your P is equal to R into W. So we are interested in this weight matrix, and this particular relation is giving us, so this particular relation is saying that we will have a unique W matrix for a particular process. And that W we can obtain by inverting R on both the sides, as long as your R is invertible. Okay, so this is how our Euler-Walker equation will help us. We'll take an example for using this particular thing. A small example we'll take when we solve the questions. And after that, we briefly introduced another important process, random process, that is known as Markov chains. So these Markov chains are also known as discrete time Markov chain, or DTMC. And when we are saying Markov chain, we in this particular course will be considering discrete time process. And Markov property, what it says is, so what we are having is here, if you observe carefully, your current output is depending on your previous outputs and previous inputs as well. So what this Markov does is, it takes, or the process, let's say x of n is your Markov chain, And this Markov chain can take values from a state space, let's say S. And this state space S can be of finite, can be finite or can be infinite. It's okay. And each entry in a state space, well, let's say S, is called a state. And this is like an evolving process. So this xn should ideally, let's say for any process, should depend on x of n minus 1, x of n minus 2, and so on. But for Markov chains, x of n depends only on x of n minus 1. Okay, so what it says is probability of x of n equal to some state, let's say xn, given x of n minus 1 equal to x of little x n minus 1, x of n minus 2 equal to x of n minus 2, and so on. This will be equal to basically probability that x of n equal to xn given x of n minus 1 equal to xn minus 1. So it says that this particular thing is independent of whatever is happening before its previous event, previous transition. So this particular thing only depends on a state or the process value just before that, and it has nothing to do whatever happens before that. Okay, so this is like this is known as Markov property. Okay, now this Markov chains can be represented. Let me delete this. I want a blank page. So this Markov chains are represented by a state transition matrix. That is, let's say matrix P. So this P will be some matrix. Let's say this is its ith row and this is jth column. So this particular entry will be Pij. Okay, so this entry Pij is basically the transition probability or the conditional probability that your xn plus 1th state takes value j given your xn had taken value I. So this is basically your transition probability. From state I to state j. So this is known as your state transition matrix or probability transition matrix. Anything is okay. And okay, and another way of representing Markov chains is known as state transition diagram. So another way of representing Markov chain is known as state transition diagram. So instead of spending time on state transition diagram right now, we will take examples for this. we will see some examples of this. So we ended with Markov chains for this particular week at this point. However, there will be much more discussion regarding to this in the coming week. So that's all about the content that was covered in this particular week. If you have any questions, then feel free to ask. Otherwise, I'll quickly move on to the questions that I have planned to cover today. Okay. So it's okay if you people don't take notes while this lecture. I'll be uploading all of these things in the drive and the link is already available to you on the website. Every week, just after the tutorial in half an hour, I'll upload this PDF of notes and in the drive and the lecture, recorded lecture on my YouTube channel. Again, the link is there in your sheet that is shared to you. Okay, so if there are no further questions, I'll quickly move on to the tutorial questions that I have planned to cover today. Okay, so like every week, this week's questions are also a mixture of past year's assignment and some new questions. So first 5 questions are past year's assignment, and remaining are the questions which are there, which I have found out from other sources or created on my own. Okay, so let's start with the first question. So it says that given a Whitson stationary random process xt with PSD sxx of f, so we have a random process xt and we know that this is a Whitson stationary process and its PSD is sxx of f. This is given to us. Now this random process is passed through an LTI system and that gives, so that this is passed through an LTI system to generate another random process, that is YT. So what we need to do is we need to find the PSD of YT. So we want PSD what is the PSD of output process. Now this is an LTI system, and to characterize this LTI system, the only thing that we need is its impulse response. So let's say this LTI system have an impulse response as h of t. So let the LTI system have the impulse response ht. And what do you mean by impulse response? So you have, so this impulse response is basically you have this system, same LTI system, and if you give impulse, unit impulse as an input, so this is unit impulse as an input to this system, then you will observe h of t, and this is known as impulse response. And why an impulse response? So this is basically, so this thing here is basically response of the LTI system or of the system to unit impulse as input. Okay, so these things we know from our signals and systems course. So these things we know. Okay. So this is the knowledge that we are having here, and this is an LTI system, and for any LTI system the output is obtained by convolving the input with your impulse response. So this y of t will be basically equal to your xt convolved with h of t. This h of t is not a random function. It is not a random process. It is a constant deterministic system function. We know it very well. Okay, and let's say this h of t have its Fourier transform as h of f. Okay, this x of t has PSD sxx of f, and this y of t has PSD syy of f. And we need to figure out the relation between syy of f, sxx of f, and h of f. Okay, so this is what we know for now, and by definition of convolution, we know this y of t can be written as integral minus infinity to infinity x of tau h of t minus tau d tau, and we can also write this as minus infinity to infinity x of t minus tau h of tau d tau. Okay, these are the things that we know. So, but now what we need to find out is uh, the what is your syy of f. Okay, so another thing that we know is this syy of f is basically your Fourier transform of ryy of tau. This is an LTI system, and we are giving a Whiteside stationary process as an input. We'll get a Whiteside stationary process as an output. So this ryy of tau and syy of f are Fourier transform pairs. So this we can write as integral minus infinity to infinity ryy of tau into e power minus j 2 pi f tau d tau. And what is this ryy of tau? This ryy of tau is nothing but expectation of y of t into y of t plus tau, or y conjugate of t plus tau. Okay, so let's take this up now. So we have expectation of y of t, or let's simplify this. Let's consider it as a real process. So we have y of t. How do we write this y of t? This y of t is basically integral from minus infinity to infinity x of t minus v, let's take different variable for now, into h of v dv, and y of t plus tau will be integral minus infinity to infinity x of t plus tau minus u, let's say, into h of u du. Okay, so this is the definition of your autocorrelation function. Now let us take these integrals common. So let's keep this expectation sign outside. Then we have integral minus infinity to infinity, integral minus infinity to infinity, x of t minus v into x of t plus tau minus u. This we have. Then we have h of v into h of u du dv. And then we can take the expectation inside by linearity property. So integral minus infinity to infinity, integral minus infinity to infinity, we have expectation of x of t minus v into x of t plus tau minus u, and this hv and hu are constant, so we have hv into hu du dv. Okay, and what is this thing here? So this is basically like x of t1 into x of t2. So this should give me rxx of t2 minus t1, which comes out to be equal to rxx of t plus tau minus u minus t plus v. So this comes out to be equal to rxx of tau minus u minus v. Okay, so this cancels out. We have this tau coming here. Then we have minus v plus, minus u plus v. Let's take the minus sign outside. So we will have u minus v inside the bracket. So this is what we are having right now. So let us substitute it here. So what will we get? We'll get integral minus infinity to infinity, integral minus infinity to infinity, Rxx of tau minus u minus v, h of v into h of u du dv. So this is the final thing that we can do with this particular equation. But we know another relation, that is this particular equation here. That is your syy of f is Fourier transform of your ryy of tau. And this is the equation that we have here. So what we will do, we'll substitute this thing in our equation number 1. So substituting 2 in 1, what we get is syy of f. Again, if you look at this particular thing, we had found out expectation of y of t into y of t plus tau. This particular integral what we have obtained here is independent of t, which means that again this is a Whiteson stationary process. So that is an important thing that we should look here. So this, I'll just make a note of it. This is independent of t. Which means that this is Whiteson stationary. Okay. So now let's take this syy of f, which we had written as integral minus infinity to infinity ryy of tau into e power minus j 2 pi f tau d tau. Now we'll substitute this ryy of tau. Let me change the color, make it red. So let me substitute equation 2 here. So we will have integral minus infinity to infinity, integral minus infinity to infinity, Rxx of tau minus u minus v, h of v into h of u du dv multiplied by e power minus j 2 pi f tau d tau. So this is what we are having here. What we will do, we'll change the order of integration. So we'll take this integration here and both of these outside. So what we get now is something like this. So we will have integral minus infinity to infinity, integral minus infinity to infinity here. Then we will have this particular integral. Let's write it in this way. Integral minus infinity to infinity Rxx of tau minus u minus v. And let us take this part also. This thing here to e power minus j 2 pi f tau d tau. So all the functions of tau, we'll just bring it at one place. And then we have this thing, h of v into h of u du dv. Okay, so we have this now. Now let us just look at, or let us focus on this particular integral inside here. So this is like a Fourier transform of this quantity. So to do that, let us substitute tau minus u minus v as something, let's say tau tilde, which means that my tau is equal to tau tilde plus u minus v, and d tau is equal to d tau tilde. So this particular integral now becomes minus infinity to infinity. So limits won't change. Rxx of tau tilde into e power minus j 2 pi f tau tilde plus u minus v d tau tilde. Then this thing is equal to integral minus infinity to infinity Rxx of tau tilde into e power minus j 2 pi f tau tilde. So this particular part, so if I take this part, this is independent of tau tilde, I can take it outside. So I can close this integral here, multiplied by e power minus j 2 pi f u into e power minus j 2 pi f minus v. And this particular thing here, whatever we have obtained, is equal to Fourier transform of autocorrelation function of your process x of t. So this comes out to be equal to sxx of f into e power minus j 2 pi fu into e power minus j 2 pi f into minus v. So now let us substitute this back in our equation here. So what we have now, therefore sxx of f, sorry, syy of f now comes out to be equal to, these red integrals are there already, so we'll have minus infinity to infinity, integral minus infinity to infinity. Then this blue thing here inside the bracket can be entirely replaced by whatever we just derived, that is sxx of f into e power minus j 2 pi fu into e power minus j 2 pi f of minus v. And then we have h of u into h of v du dv. Now this particular thing here, this sxx of f is a constant, so I can take it outside. So this thing I can completely take it outside because it is a constant. It is not a function of u and v. So this is what we are getting right now. Another thing is this e power minus j 2 pi fu and this h of u, these things are only a function of u. These are not function of v. And similarly, this particular thing, which I will be highlighting in green, is only function of v. And this integral here, this thing is with respect to u and this thing is with respect to v. So whatever is function of v, I can simply take outside this particular integral. So what we now get is sxx of f into integral minus infinity to infinity h of v into e power minus j 2 pi f minus v dv multiplied by integral minus infinity to infinity h of u into e power minus j 2 pi fu du. Okay. Now by definition of Fourier transform, this particular thing here is simply my Fourier transform of h of u, that is h of f, capital H of f. And similarly, this particular green part, whatever we have here, so you observe this is very similar integration. The only change is we have minus v here instead of plus v. So this thing is basically my Fourier transform, again h of f. So this particular thing, let's say this minus v I can write as minus f into v. So this is like evaluating the Fourier transform at minus f. Okay. So what we get here is sxx of f into h of minus f into h of f. Now what we have is our system h of t is real. And we have conjugate symmetry for the Fourier transform. So for a real LTI system or a real impulse response h of t, we have h of minus f is equal to h conjugate of f. Therefore, this syy of f comes out to be equal to sxx of f into h conjugate of f into h of f. So this comes out to be equal to magnitude of h of f square into Sxx of f. So therefore what we have obtained is, therefore the PSD of the process, or of the output process yt is Syy of f equal to magnitude of h of f square into Sxx of f. Is it clear? Any questions? So this is the final answer that we have. Any questions here? Okay, if there are no questions, then I'll quickly move on to the next question. So you can stop me at any point to ask questions. Please unmute yourself and ask, because I can't hear or I can't see the chat box. Okay. So next question says, if a random process xn can be generated using linear combination of its past values and innovation component, then it is an dash process. Okay, so what we are having here is, what is given to us is, we have a random process xn. It says that it can be generated with using a linear combination of its past values. So this xn can be generated by linear combination, let's say k equal to 1 to m of its past values and an innovation component. So linear combination of its past values and an innovation component. This is innovation component. And this is simply your linear combination of past values of x of n. So this is linear combination of past values of xn. So if we observe carefully, when we were discussing the processes, we had looked at this particular thing. We had seen that an autoregressive process can be written as, so this xn. So if I shift this entire thing to the right hand side, so it will be equal to sum of a linear combination of the past values of the process plus an innovation component. So this v of n is also known as the innovation component. So let me just add it here. So this is also known as innovation component. Okay. So therefore, this particular structure that we are having here So this structure is for an autoregressive process of order m. So this is for autoregressive process, and to be specific, this will be of order m. This is just definition chasing. This we have already seen. Just a simple question from last year's assignment. Any questions? Okay, if there are no questions, then let me quickly move on to the next question. So the next question is, a moving average random process can be generated by passing a white noise through an dash filter. And here options are all pole filter and all zero filter. So first of all, let me just tell what is an all pole filters. So first thing, all pole filter, it means that, so okay, first let me define what are poles and zeros, assuming some people might not know this, but let me just define. So what we will do is, let's take discrete process. So this h of z, so this is the transfer function or system function, or let's say not write this, z transform of impulse response of LTI system, and this can be written as a rational function where I'll have a numerator polynomial, so L equal to 0 to m al into z to the power minus L, divided by a denominator polynomial, let's say k running from 0 to n bk z to the power minus k. Okay, so this is a standard representation for z transform of any LTI system, any discrete time LTI system. Now, roots of numerator polynomial, so roots of numerator are known as zeros. And why is it so? Because if we substitute z equal to the roots in this particular equation, you will get h of z equal to 0. Similarly, roots of denominator polynomial these are known as poles. So if you substitute z equal to the one of the root, let's say x, z1 is a pole of this particular transfer function, then if you substitute h, or if you look at the value of h of z1, then it will be infinity because your denominator will be 0. So it's like a pole, it's shooting its value to a very large value like infinity. So in that situation, that's why we call these roots of the denominator polynomial as poles. So now we have, or now we know what are poles and zeros of a transfer function. So next thing that we need to know is what are all zero filter and all pole filter. So first thing we'll look at is the all zero filter. So it means that no poles exist, only zeros exist. So what it means, so from this equation, your B0 will be equal to 1. So this implies that B0 equal to 1. And another thing that you will have is your BKs or BK for all K equal to 1, 2 and so on till n. So in that situation, your h of z will appear something like this. So this has only poles, only zeros and no poles. So such kind of filter is all zero filter. Next thing that we need to look at is all pole filters. So here it means that no zeros exist. Only poles exist. And here what we will get, we'll have A0 as 1 and A1, A2 or let's say AL equal to 0 for all L equal to 1 and so on till N. And this h of z for this particular filter will look at 1 over summation k running from 0 to n bk into z to the power minus k. So this is how the impulse response, Z transform of the impulse response look for an all pole filter. So again here we have only poles. So now our idea of all zero filter and all pole filter is clear. Now let's get back to the question that we are asked. So it says that a moving average random process can be generated by passing through a white noise through an dash filter. So let's look at what is the moving average filter. So for a moving average filter, we have our x of n equal to Vn plus summation k running from 1 to capital K bk conjugate z to the power minus k. So okay, let's not confuse. Okay. So this is what we are having. Now if I take z transform on both the sides, v of n minus n. If I take z transform on both the sides, then this will be x of z, which will be equal to vz plus summation L equal to 1 to k bl conjugate, and this v of n minus L will be basically z transform of v into z to the power minus L. This comes from the properties of z transform. You can look at it in the in your signals and systems course. Now I can take v of z common and divide by it on both the sides. So we'll get something like this: 1 plus summation L equal to 1 to k b of L conjugate into z to the power minus n. Another thing to note here is this transfer function is output z transform upon input z transform. So this is ratio of output z transform to input z transform. So this is your output and this is your input. Okay, so this is basically your h of z. So now if you observe that only a rational function exists, only a polynomial exists. It is not a polynomial by polynomial kind of structure. So we are having polynomial only in the numerator and the denominator is only 1, which means that the concept of roots will exist only for this particular thing here, which means that in this particular equation only zeros exist, no poles exist. So this exactly resembles the way we have our Z transform here. which means that this is an all zero filter. So this thing here is an all zero filter. Is it clear? Any questions? So the correct option to this particular question is all zero filter. Any questions?
Ma'am, I do not have any question. Actually, I am very new, but you are, and I am, due to some network, I am listening few slides and few have skipped. So I am sorry, I have no
Okay.
question.
Anyway, you can see the recording. It's okay.
Yeah,
You
yeah,
can see the
I will
recording,
see.
and if you have any doubts, you can put it in the Q&A. So whatever doubts related to my session, I'll answer there.
Thank you, thank you.
Yeah. You can see the notes and all those things. You can ask the queries in the Q&A session. It's Q&A part. It's okay. Yeah.
Okay.
Okay. So let's move on to the next question. This is also an assignment question. Okay. So here what is said is, given that xn is a first order autoregressive process such that expectation of x of n into x conjugate of n is sigma, and expectation of x of n into x conjugate of n minus 1 is rho, then find the variance of its innovation component. Okay, so what we have here is x of n, or if we have, let's write it properly. So for order 1 autoregressive process, we can write xn as something, some coefficient or some weight into x of n minus 1 into the innovation component. Now I can write this innovation component as x of n minus a times x of n minus 1. And what we need to find is the variance of this noise. So therefore, variance of v of n we can obtain as expectation of, or instead of doing that, what we will do is we'll go to the notes that we had taken earlier. Let's not repeat the derivation because we are already quite out of time. Yeah, okay. So we had found for an autoregressive process, we had this particular relation. This particular relation we had, that is variance of x is equal to magnitude a square sigma x square plus variance of noise. So let us directly use that thing. So what we have is expectation of magnitude of xn square is equal to mod a square into expectation of magnitude of xn square, or x of n minus 1 square plus variance of innovation component, let's say variance of v of n. So we can write this xn equal to a times x of n minus 1 plus v of n. Okay, so what we get is, let's say this is given to us as sigma, then we have mod a square into sigma plus variance of innovation component, that is v of n. So therefore variance of v of n comes out to be equal to sigma into 1 minus magnitude of a square. So this is the first thing that we are having here. Now we need to figure out what this a is. Now what we will do is we'll go to Euler-Walker equations. So this is the Euler-Walker equation that we are having here, like this. And just reduce its size and keep here. So this is the Euler-Walker equations. Now the weights that we have is only one here. And again, for what we can do is, for this only one weight, we will get something like this. Rxx of 1 will be equal to Rxx of 0 into A. Okay. So this Rxx of 1 is basically your expectation of x of n into x conjugate of n minus 1. And this is basically your variance, that is sigma, given to us into A. So and this thing here, expectation of xn into x conjugate of n minus 1 is given to us as rho. So therefore what we get here is rho equal to sigma A. Therefore A comes out to be equal to rho by sigma. Now we'll substitute this in equation 1. So therefore variance of V of n, or the innovation component, which is equal to, I think I made some mistake. No, it's okay. Which is equal to sigma into 1 minus magnitude of A square. So this comes out to be equal to sigma into 1 minus A square, magnitude of A square will be mod rho square upon sigma square. So sigma is a real value, it is a variance. So this comes out to be equal to sigma into sigma square minus magnitude of rho square divided by sigma square. So this comes out to be equal to sigma square minus magnitude of rho square by sigma, and this is the final answer that we are having. So this is the value of your variance of innovation component. Okay. If you have any questions, just stop me and ask. If not, I'll move to the next question. So the next question says, in a Markov chain with a state transition matrix P, the state J is said to be accessible from state I if. So this is a definition, and the answer to this is P to the power n I equal it's I comma jth entry for some n is not equal to 0. So this is a definition for accessible state. So it says that state J is said to be accessible from state I if there exists an n such that P to the power n, let's say this is P1, and P1's I comma jth entry is not equal to 0, which means that so this is also a transition matrix. So it says that there exists a non-zero probability that we will move from state I to state J. Okay. So I think this concept will be discussed in detail in coming week. But for now, just take this as a definition of accessible states. I don't want to get into details of Markov chains for now. Just take this as a definition. Okay, so this third option is the correct option. If you have any questions, then let me know. Otherwise, I'll move on to the sixth question now.
Move on, man.
Okay. So the next question says that draw the system realization diagram for AR process. So there were some diagrams that were shown in the lectures. However, there was no discussion on how these diagrams were made. So I just added uh, it as a question just to make the understanding of the diagram clear. So let's do that. So for AR process, let's say of order M, we can write x of m or x of n as or x of n plus summation I equal to 1 to m ai conjugate x of n minus I, and this comes out to be equal to v of n. And we want to realize this particular equation or this particular system equation. So basically the current instant is your nth instant and all of these are your past outputs, and this we know. Okay, so basically we want to build or we want to obtain my Rx of n as a linear combination of your innovation component and all the past outputs fed back to the input. Okay, so your V of n is your input. So this is your V of n. So V of n is your input and your output is x of n. Okay, so this x of n, or let's say a delayed, so this z inverse is the unit delay block, and let's say, okay, let's not complicate. Let's say if I have something like this, then this will give me a gain of a. Okay, so now what happens is this thing is passed through a delay block. This will give me x of n minus 1, and x of n minus 1 is multiplied by minus of a1 conjugate. So you have minus of a1 conjugate here. So it will get multiplied by minus of a1 conjugate. And then this gets added to your xn and your v of n. So what I have now is v of n minus a1 conjugate x of n minus 1. But we have more terms. So then we have z inverse here. This will give me x of n minus 2. So here I have x of n minus 1. I'll delay it by 1 unit. So this thing is adder block. So this I have, and then this gets multiplied by minus of a2 conjugate and again gets added. And in this way we will have total m such things. So here we will get x of n minus m. X of n minus m gets multiplied by minus of am conjugate. Okay, so you have your input here, then you have your output, and the delayed versions of your output are multiplied by the appropriate gains and are fed back, oh sorry, and are fed back to your input. So this is the realization diagram for your AR process of order M. Okay. Now similarly, let us repeat this same process for another thing, that is your MA process or moving average process. So for a moving average process, what we had, our output Excel was given as Vn plus summation k running from 1 to, or let's say L running from 1 to k, BL conjugate into V of n minus L. Again here input is Vn and output is Xn. So we have input Vn here and then we have output X of n here. Okay, so this is what we are having. So this V of n gets added. Let me take it this out. So this V of n is delayed by 1 unit. Then it gets scaled. It gets scaled by B1 conjugate, and whatever output we have gets added to your Vn. So this here what we will get Vn plus B1 conjugate into Z inverse. But we have k such terms. So then we'll have another delay block. Then that will get multiplied by B2 conjugate. That again will get added here. Now similarly, we'll have to repeat this thing k times. So what we have here, we get V of n minus 1. Here we get V of n minus 2. And here we had in input V of n minus m minus 1. And here we will get V of n minus k, sorry, not m, k. Okay. And then this will get multiplied by B of k conjugate. And these things will get added. So basically we'll have something here which is like this. So this is the representation for so a tilted version of this particular thing was done. However, this is what we are having here. So this is the representation for your moving average process. Okay. Now in similar way, let us repeat the same thing for the ARMA process. And for ARMA process or autoregressive and MA process, what we have is X of n plus summation I equal to 1 to m AI conjugate X of n minus I. This is equal to V of n plus summation I equal to, or let me change, L equal to 1 to k B of L conjugate into V of n minus L. Okay. So then I can write X of n as V of n plus summation L equal to 1 to k V of L conjugate V of n minus L minus summation I equal to 1 to m AI conjugate X of n minus I. So let us try to have this. So this particular part is input and its delayed versions, and this particular part is feedback. So let's try to draw. I'll just copy paste this equation next page. So what I'll do, I'll just again do some sort of color coding. So let's say this particular thing is in green. Okay, so let's start with input. So my input was v of n, and this v of n was input, and we had output as x of n. Let's first do this part here. So this v of n gets added, and one more thing that we'll consider is m is less than k. We'll take this particular case. You can do the same thing for opposite case. So we'll have a z inverse, then we will have a gain multiplied of b1 conjugate will get added here. Same way, same thing what we had done earlier. Then we will have z inverse b2 conjugate, and you can add it here, and you can repeat the same thing k times. So I'll have so this will be b of k minus 1 conjugate, and this is b of k conjugate. And this thing, let's say entirely is x1 of n. So this is what I'm having here. So this is my x1 of n, and this gets added to this green component like this. And then after adding and everything, this will give me my output x of n. Okay, and what is this green part now? This is basically a delayed version. So this is x of n minus 1. You scale it by minus of a1 and then add it like this. Similarly, z inverse, you scale it by minus a2 conjugate and add it, and so on. You repeat the same thing m number of times. So we'll have minus of am conjugate here. Okay, so this particular representation is called direct form 1. This is an inefficient way of doing this thing, because why? This particular thing here is one system, this particular thing is another system, and all of these are having delay elements and delay elements here. So what we can do is systems or convolution is commutative operation. So we can interchange these systems like this. So we can interchange the order of these two. We can interchange the order of these two to get direct form 1. So we will interchange the two systems. So this is your h1 and h2, h1 and h2 to get direct form 2 representation. Okay, So let me just copy these things. Let's take this thing. Just like this here. Let me delete this. Let's keep it. And let me again copy this second system. Like this. Okay, so this is what we are having right now. And input to these are anyways same. So input to this is v of n and output here is x of n. Now what we will observe here is the signal that is here is going in this direction and this direction also. So whatever is signal here and here is exactly same. What is here and here is exactly same. So what we can do is we can simply merge these two and remove the excess delay blocks. So what we will do now, remove additional delay blocks to get final structure. Okay, so how will the final structure look? We have v of n that gets added. So this structure will repeat as it is. And then we will have delay blocks. Something like this. Okay, and then what we will do is first let us construct this green structure. So we have this Z inverse. This will get multiplied by minus of A1 conjugate like this. Then here we will have minus of A2 conjugate. And what we have assumed is my m is less than k. So this m is less than k. So we'll have, let's say this is the kth thing, minus of ek conjugate like this. And then at the end we will have minus of am conjugate. Okay, and now we'll replicate this red part. So first thing we will have is p1 conjugate. So just add it here, and this will give me my x of n. Then here we will have p2 conjugate. We'll add and like this here, and so on. And here the last one will be my bk conjugate. So this is the final direct form to structure. This was shown in the lecture. Okay, any questions?
No, ma'am.
Okay, just a minute. Okay, if there are no questions, then let me move on to the next question. So this is second last question that I have planned to cover today. So it says that consider the Markov chain with three states, 1, 2, and 3. That has the state transition matrix or probability transition matrix as P, which is given here. So this is the state transition matrix given to us. These are the three states that we have. And we want to draw the state transition. First thing that we need to do is we need to draw the state transition diagram for this. And then there is another question that we need to solve. But let's start with this. Let's start with drawing the state transition diagram. Okay, so what is your state transition diagram? Or rather, how to do is what we do is we have some states and then we show the probability with which we'll go to the another state given we are at that particular state. So basically this I or ijth entry of this matrix is given by probability that, let's say this Markov chain is xn. So xn plus 1 is at jth state given xn is at ith state. Okay, so the matrix that we are having here is something like this. So this is the direction of my I, this is the direction of j. So this first entry will give me a transition probability that you are in state 1 and you go to state 1. Then the second one will give me a transition probability that you are at state 2 and you go to state 1. Third entry will give me transition probability that you are at state 3 and you will go to state 1. Then in second row, this will give me a transition probability that you are at state 1 and you go to state 2. This is second entry will be you are at state 2 and you go to state 2. Then third entry will give me you are at state 3 and you go to state 2. Similarly, in the last row, you are at state 1 and you go to state 3. Am I making some mistake? I think so. Wait a minute. So this is basically you are at state 1, I, and you go to jth state, Pij 1. Then this is 1 to 2 and this is 1 to 3. 1 to 2 then 1 to 3. Yeah. Then here you are at state 2 and you go to state 1. Here you are at state 2, you go to state 2. You are at state 2 and you go to state 3. Similarly, here you are at state 1, you go to state 3, you go to state 1. Here you are at state 3, you go to state 2. And here you are at state 3, you remain at the state 3. So given to us is this probability 1 to state 1 is half. Then this is 1 by 4. This is also 1 by 4. Then this is 1 by 3. 2 to 2 is 0. And 2 to 3 is 2 by 3. And then 3 to 1. 3 to 1 is half. 3 to 2 is also half. And 3 to 3 is 0. So let us try to draw this diagram. So we have three states. That is 1. Let's draw it like this. You have state 1. Then you have state 2. And you have state 3. Okay. So with probability, so first thing that we need to look at is you remain at state 1. And that is with probability half. Then from state 1, you go to state 2 with probability 1 by 4. Then from state 1, you go to state 3 with probability 1 by 4. Okay, then let's move on to the second state. From state 2, you go to state 1 with probability 1 by 3. Now state 2, you remain at state 2 with 0 probability. So this there is no need to draw this particular branch because it is of 0 probability. You won't go to that state, or you won't remain at state 2. So then you have state 2 to state 3, and that is with probability 2 by 3. And at the end, you have from state 3, you go to state 1 with probability half, this one. Then from state 3, you go to state 2, again with probability half. And from state 3 to state 3, you remain at state 3 with probability 0. So this is basically your state transition diagram. So just to complete, I'll just add, there is no need to draw this branch. This is with 0 probability, and similarly, remaining at state 3 is also with 0 probability. So you don't need to draw this. Okay, so this is your state transition diagram. Okay, now once we have this state transition diagram, there is another question that is asked to us. So it says that we know that probability of x1, so first state probabilities are prior probabilities are given to us. The probability of x1 equal to 1 is equal to probability of x1 equal to 2 equal to 1 by 4. So from here what we can calculate is probability that x1 equal to 3 will be equal to 1 minus, because there are only 3 states, probability of x1 equal to 1 minus probability of x1 equal to 2. So that will come out to be equal to 1 minus 1 by 4 plus 1 by 4. That comes out to be equal to half. But what we need to find out is probability of x1 equal to 3, x2 equal to 2, and x3 equal to 1. So this joint probability we need to figure out. So we need to find probability that x1 equal to 3 and x2 equal to 2 and x3 equal to 1. So basically this is intersection. So when we have comma separated, this implies intersection. Okay, so another thing that we can write or we can note here before solving is probability of A intersection B. We can write as probability of A given B into probability of B. Similarly, probability of A intersection B intersection C, we can write as probability of A intersection B given C into, or what did I do here? Sorry, not like this. Probability of A given B intersection C into probability of B intersection C. So these things are coming from the definitions of conditional probability. Just look into it once. So this thing here, probability of x1 equal to 3 into x2 equal to 2 into x3 equal to 1. What we can do is we can take the most recent state, that is x3, write this as probability that x3 equal to 1 given x1 equal to 3 and x2 equal to 2 into probability that x1 equal to 3 into x2 equal to 2. Okay, now this is a Markov chain. This is a Markov chain. So this x3 depends only on x2. So this particular probability is equal to probability that x3 equal to 1 given x2 equal to 2. Okay, so this we can simplify as probability that x3 takes 1 given x2 equal to 2 multiplied by probability of x1 equal to 3 and x2 equal to 2. So now we can again apply this particular property here. Now x2 is the most recent state, so keep it as it is. And condition it with one state prior. So this is equal to x2 equal to 2 given x1 equal to 3 into probability that x1 equal to 3. So these are immediate state transitions. So therefore from state transition diagram, We know that from state transition diagram, probability that xn plus 1 equal to j given xn equal to I is the I comma jth entry. So this will be basically P of 2 comma 1 or 2 1. Then this particular thing here will be P of 3 2 or 3 comma 2th entry into probability of x1 equal to 3 we have obtained as half. Now what is 2 comma 1th entry of your state transition diagram? 2 comma 1 is 1 by 3 into 3 comma 2 is 1 by 2 into 1 by 2. So this comes out to be equal to 1 by 12. So therefore this probability that x1 equal to 3, x2 equal to 2 and x3 equal to 1 comes out to be equal to 1 by 12. Okay. So this is the final answer that we have. If you have any questions, then let me know. Otherwise, I'll move on to the last question.
Okay, ma'am, move on.
Okay. So this is the last question for today. So this says that consider a binary symmetric channel with crossover probability SP. Let probability, or these are the prior probabilities, probability of 1 equal to 1 and probability of 0 equal to 0. So let me make clear, these are the prior probabilities. So these probability of initial, or let's say state 0 probability or state 1 probability is Q. What we need to do is we need to represent this as a Markov chain. We need to find the transition matrix, state transition matrix, and draw the state transition diagram. So what do you mean by a binary symmetric channel? So binary symmetric channel will have two inputs, 0 and 1, and then we have output 0 and 1. Okay. Then we have the crossover probability. Crossover probability means your 0 goes to 1 with probability P and 1 goes to 0 with probability P, and it remains in the same state with probability 1 minus P. It remains in same state with probability 1 minus P, and it is given that the probability of initial 0 is 1 minus Q. So this is for x1 and this is Q. So this is for x1. So what does this thing here mean? This probability that x1 equal to 1 is Q. Probability that x1 equal to 0 is 1 minus Q. Okay, so how many states do we have? 0 and 1. 0 and 1. So we have two states. It is 0 and 1. Okay. So let me draw it. So we have a state 0 and we have a state 1. Now we go from state 0 to state 1 with probability P. So you are at state 0. Given you are at state 0, you go to state 1 with probability P, and you remain at state 0 with probability 1 minus P. Similarly, with probability P, given you are at state 1, you go to state 0 with probability P, and you remain at the state 1 with probability 1 minus P. That's all. This is your state transition diagram. So this particular thing is your state transition diagram. Now another thing that we need to figure out is your state transition matrix. So this is your state transition diagram here. So what it says is probability that xn plus 1 is 1 given xn equal to 0 is equal to p. Then probability that xn plus 1 equal to 1 given xn equal to 1 is 1 minus p. Similarly, probability that xn plus 1 equal to 0 given xn equal to 0 is 1 minus p, and probability that xn plus 1 equal to 0 given xn equal to 1 is probability is equal to p. So we have this p like this. So this is for your state 0, this is for your 1, this is for your 0, this is for your 1, this is for your n, and this is for your n plus 1. Okay. So you go to state 0 with you go to state 0 when you were initially at 0 by probability 1 minus p. You go to state 1 when you were initially at state 0 with probability p. You go to state 0 when you were initially at state 1 with probability p, and you go to or you remain at state 1 with probability 1 minus p. So this matrix here is simply your state transition or state or probability transition matrix. This was covered in lecture, but still I took this in little detail. Any questions?
No, ma'am. Thank you.
Okay, thank you. If you have no
Thank
questions,
you.
you are free to leave the meeting. Thank you for attending today's session.
Thank you, ma'am. Thank you very much.